In the second part of Chapter 13, we're going to look at half-lives and transmutations and radiometric dating. So when you look at radioactivity, it breaks down by half portions. So a half-life is the time needed for half of the radioactive material that's present to have broken down and already emitted. So the half-life for cobalt-60 is 5.3 years. So if you have a sample of cobalt-60, after 5.3 years, half of it would no longer be radioactive. So if you had 1 gram, a half a gram would still be radioactive and a half a gram would no longer be. And it would have decayed to whatever it was going to form, which sometimes is another element. After 10.6 years, notice that's 2 half-lives, 5.3 plus 5.3, you would have 0.25 grams of radioactive material. And every 5.3 years, you could take the amount you just had and split it in half again. And so that's a math that you'll end up doing for your radioactivity. If they tell you the half-life, after 1 half-life period, you can take the initial sample and break it down in half. And if the time is the equivalent of 2 half-lives, you can take that sample and break it in half and break it in half again. If it's 3 half-lives, break it in half, break it in half, break it in half. So you'll notice each time you just split it in half, each time you pass through a half-life. There is a way to mathematically do that. We're not going to worry about the whole equation for doing that at this level. We'll just always give you a full half-life amount, whether it's 1 or 2 or 3 or 4. And you can just divide the quantity in half that many times. When a radioactive element emits an alpha or beta particle, the atomic number is going to change. Now, not every radioactive substance is going to emit an alpha or beta particle. Some of them just emit gamma, and if they do, you get the same thing out at the end. But they'll often use those gamma emitters when they're looking at your medical diagnostic sort of radiation. They'll put those in, the gamma releases, it goes down in energy, and then it shows what you need, and it's not releasing alpha or beta particles into your body to cause damage. When you get an alpha or beta particle coming off, you get a different element out, and that's because your alpha particle is removing 2 protons, 2 neutrons from the nucleus. And your element identity is based on the number of protons. So if you take out 2 protons, you're going to get a different substance out. And that's called transmutation, when you change from one element to another element. And that only happens in nuclear chemistry. That doesn't happen in regular everyday chemical reactions. Only when there's a nuclear chemistry reaction that occurs. So if you get a beta particle coming out, well, that's just an electron coming out. Now, electrons don't exist in the nucleus, so you would think that wouldn't affect what kind of element you have, but if you remember, the neutron breaks apart into 2 different things. It breaks apart into an electron and a proton. Now, our element identity is based on the number of protons. So when you emit a beta particle, you're upping the proton count by 1. So it will turn into the next element on the periodic table. So if it was carbon to begin with and it emits a beta particle, you'll end up with nitrogen, the one next to it, after it has emitted. And so they move over 1. The ones that emit alphas are losing 2 protons, so it actually goes down 2 elements. We have natural transmutation. There's a lot of radioactivity found in nature, and when they emit, they change into another element. So for example, carbon-14 is radioactive. And when it emits a beta particle, it's going to move 1 to the right, and you get nitrogen-14. And that's what we actually use in our carbon dating, and we'll talk about that a little later. Uranium-238 emits an alpha particle. When it does, it moves 2 elements to the left and becomes thorium-234. And you'll notice that while it moved 2 elements to the left, the number here subtracted by 4. That's because these numbers written after your elements are the mass. And the mass with a helium, one that has released helium, is going to go down by 4 because helium has 2 protons and 2 neutrons, so a total mass of 4. And so it will subtract a mass of 4. You'll notice the carbon here, that number didn't change. The reason as carbon 14 goes to nitrogen 14, the reason that number doesn't change is you've emitted an electron, but a neutron is turned into a proton. So we lost one for the neutron, but we gained one for the proton, so the mass doesn't really change. Remember, electrons don't weigh a whole lot. And so as it leaves, you don't see a really appreciable change in mass. And so the carbon 14 just becomes nitrogen 14. So when you have your alpha particle emitting, you're going to go down in mass by 2. You're going to move over to the left 2 elements on the periodic table, and that'll be your product. When you have a beta particle coming off, you move 1 element to the right, and the mass remains the same. So the alpha particle has that mass of 4 and an atomic number of 2. So it has 2 protons and a mass of 4. It's often written as a helium, helium-4 because of that. When it emits the alpha particle, you remove 4 from the mass and 2 from the atomic number, and that gives you your new isotope. And you can look up the new isotope on the periodic table, or you can just count over 2 to see what it is. So for example, if I have radon 226, which has the atomic number of 88, I would take that 226, which is the mass, and I'm going to take away 4 because the helium that left had a mass of 4. And that gives me a new mass of 222. And then I need to subtract 2 from my atomic number because 2 protons left. And that gives me an atomic number of 86. Now if I look on the periodic table for an element with the atomic number of 86, I get the symbol Rn, so that will be my product. So we're able to figure it out doing the math. Beta particles have a mass of 0. It's not really 0, the electron has mass, but it's just so small that it doesn't affect the mass that we see. So the atomic, when they write them, they often write the atomic number as -1 because we're going to subtract a -1. In other words, we're going to add a proton to the atomic number. So, because when you subtract a negative, it becomes positive. The symbol is often written 0 - 1 electron. And what happens there is you take your mass number and you don't change it at all. You subtract 0. You haven't really taken a mass, appreciable net mass from the nucleus. So it remains the same. But you take your atomic number and you subtract a -1, which is the same as adding 1. You add 1 to it because you just gained a proton. And you get a number that's 1 higher. If you look on the periodic table for atomic number 54, you'll see the symbol is Xe, and that's what you'll put in as the symbol of your product. So you'd put these numbers and symbols in for the AZX in your product for a beta particle. So try to complete, just pause the video and see if you can complete what your products would be for both the alpha particle releasing and the beta particle releasing. Make sure you have your periodic table on hand. You'll need it to find the symbols. And see if you can predict what you would get for all those question marks there for your symbol. And the reason you're doing this is you'll have questions like this on the midterm, and you will also possibly have them on the quiz. So making sure you know what you're doing here is going to be really important. There's the answers for it. So artificial transmutation is something that has happened more recently, where in a laboratory we create nuclear changes and create elements that actually don't exist in nature often. Ernst Rutherford was the first to do artificial transmutation. He didn't really mean to. but he was trying to do something else, and he ended up with this happening. So in 1919, he took an alpha particle and collided it with a nitrogen atom, and he got oxygen 17 and hydrogen. That wasn't what he expected, but it did teach the first step of how we could do this. And since then, we've had a lot of various artificial transmutations that have been formed in the laboratory. And some of them have even won Nobel Prizes. There's one called Nobelium just because they were really hoping to get a Nobel Prize for creating it. So elements 93 through 118 on the periodic table are all formed since that time by artificial transmutation. And many of them are named after the reactors where they accelerated them and collided them to form the new particles in some way or another. There's like Californium because there's one located in California, things like that. There's also a natural one that happens from the sun's energy. It comes down, and in our outer atmosphere, it affects the neutrons that are coming in from the sun. And those neutrons hit nitrogen. And when they hit nitrogen, they turn into carbon-14. This carbon-14 reacts with oxygen to make carbon dioxide. And plants, you'll remember we breathe out carbon dioxide. Plants suck in carbon dioxide, and so plants will sometimes absorb a small portion of carbon dioxide that has carbon-14 from the atmosphere. And then we eat the plants, or the animals we eat the plants. And once an animal or plant is dead, it stops eating food or absorbing carbon dioxide. And so the amount of carbon-14 doesn't increase anymore. And because it's radioactive, it slowly decays, has a longer half-life, and so it takes a while for it to decay. And we can look at the amount of carbon-14 still present and do the math backwards and figure out how long it's been since whatever it is died, how many half-lives have passed, how much of our carbon-14 has disappeared. It has a half-life of 5,730 years. So much longer than our lifetime, but shorter than the age of the Earth. So it works for dating to a certain point, and then you get to such a low portion of radioactivity that it's really not all that useful anymore. So we can use it to clock how long ago a plant or animal died to about 50,000 years. The type of radiometric dating that assumes this will work assumes that the sun has always been hitting with the same intensity that it currently is, and that the plants have always been absorbing carbon dioxide to the same rate they are right now. And that would have to be the case for the past 50,000 years for that to be the case. May not be true, may be true, so there could be a little bit of error there in the carbon dating. But so far as we know, this should be working.